Mathematics logics. One of the popular definitions of logics is that it is the analysis of methods of reasoning. In studying these methods, logics is interested in the form rather than the content of the argument. For example, consider the two arguments. 1. All cats like fish. Sylvie is a cat. Hence, Sylvie likes fish. 2. All A are B. S is an A. Hence, S is a B. The truth or falsity of the particular premises and conclusions is of no concern to logicians. They want to know only whether the premises imply the conclusions. The systematic formalization and cataloging of valid methods of reasoning are a main task of logicians. If the work uses mathematical techniques, or if it is primarily devoted to the study of mathematical reasoning, then it may be called mathematical logics. We can narrow the domain of mathematical logic if we define its principle to be a precise and adequate understanding of the notion of mathematical proof. Propositional sentence. Sentence may be combined in various ways to form more complicated sentences. We shall consider only truth-functional combinations in which the truth or falsity of the new sentence is determined by the truth or falsity of its component sentence, called propositional sentence. So, propositional sentence is a sentence that is by itself either true or false. Examples: Puppies are cuter than kittens. Party rock is in the house tonight. Propositional connective. 1. Negation. 2. Conjunction. 3. Disjunction. 4. Conditional. 5. Biconditional. Negation. Negation is one of the simplest operations on sentence, although a sentence in a natural language may be negated in many ways. We shall adopt a uniform procedure, placing a sign for negation, the symbol, in front of the entire sentence. Thus, if A is a sentence, then denotes the negation of A. The truth functional character of negation is made apparent in the following truth table. When A is true, the negation of A is false. When A is false, the negation of A is true. We use T and F to denote the truth values true and false. Next, conjunction. Another common truth-functional operation is the conjunction, and the conjunction of sentence A and B will be the divided by A and B, and has the following truth table. A and B is true when and only when both A and B are true. Note that there are 4 rows in the table corresponding to the number of possible assessments of truth values to A and B. Next, disjunction. In natural language, there are two distinct uses of or, the inclusive and the exclusive. According to the inclusive usage, A or B means A or B or both, whereas according to the exclusive usage, the meaning is A or B but not both. We shall introduce a special sign P. For the inclusive connective, its truth table is as follows. Thus, A or B is false when and only when both A and B are false. A or B is called a disjunction with the disjunct A and B. Next, conditional. Another important truth functional operation is the conditional. If A then B ordinary usage is unclear here. Similarly, if A then B is false when the antecedent A is true and the consequent B is false, their meaning is unclear since we are accustomed to the assertion of some sort of relationship, or usually causal, between the antecedent and the consequent. We shall make the confession that if A then B is false when and only when A is true and B is false. Let us denote if A then B by an expression. If A then B is called a conditional. Its truth table is as follows. The sharpening of the meaning of if A then B involves no conflict with ordinary usage but whether only an extension of that usage. A justification of the truth table is the fact that we wish if A and B then B to be true in all cases. Thus, the case in which A and B are true justifies the first line of our truth table, since A and B are both true. If A is false and B true, then A and B is false while B is true. This corresponds to the second line of the truth table. Finally, if A is false and B is false, A and B is false and B is false. Next, by conditional. Let us denote A if and only if B by slash. An expression is called a biconditional. Clearly, A if and only if B is true when and only when A and B have the same truth value. Its truth table therefore is tautology. A statement from that is always true, no matter what the truth values of its statement letters may be, is called a tautology. A statement from is a tautology if and only if its corresponding truth function takes only the values t, or equivalently if in its truth table the column under the statement from contains only ts. Example, if A and B, then A. For proof, use of truth tables. Next, contradiction. A contradiction is a statement that is always false. Example, A and the negation of A. For proof, use of truth tables. Negation. 1 is and or conditional and biconditional. Negation and. The negation of P and Q equivalent the negation of P or the negation of Q. For proof, use of truth tables. These two statements are always the same. Negation or. The negation of P or Q equivalent the negation of P and the negation of Q. For proof, use of truth tables. These two statements are always the same. Negation conditional. If the negation P, then Q equivalent to the negation of P and the negation of Q. For proof, use of truth tables. These two statements are always the same. Negation biconditional. The negation of P if and only if Q equivalent to the P and the negation of Q or the negation of P and Q. For proof, use of truth tables. These two statements are always the same. These four equivalents are called the Morgan's laws. Inverse, converse, and contraposition. If P then Q, so inverse. If the negation of P, then the negation of Q. Converse. If Q, then P. Contraposition. If the negation of Q, then the negation of P. Take off. Conclusions. Disjunctive syllogism. Hypothetical syllogism. Modus ponens and modus tollens. Rules of disjunctive syllogism. P or Q, the negation of P, therefore Q. Example, either the sun orbits the earth or the earth orbits the sun. The sun does not orbit the earth. Therefore, the earth orbits the sun. P or Q, the negation of Q, therefore P. Example, the cake has either chocolate or vanilla frosting. The cake does not have vanilla frosting. Therefore, the cake has chocolate frosting. Rule of hypothetical syllogism. If P then Q, if Q then R, therefore if P then R. Example, if 18,486 can divided by 18, then 18,486 can divided by 9. If 18,486 can divided by 9, then the sum of 18486 can divided by 9. Therefore, if 18,486 can divided by 18, then the sum of 18486 can divided by 9. Rules of modest exponents. If P then Q, P therefore Q. Example, if there is the sign in the universe, then there must have been a designer. There is the sign in the universe. Therefore, there must have been a designer. Rule of modest tolerance. If P then Q, the negation of Q. Therefore, P. Therefore, the negation of P. Example, if a world government is established, wars will cease. Wars are not ceasing. Therefore, a world government is not being established. Counter statement. In order to make the structure of complex sentence more transparent, it is convenient to introduce special notation to represent frequently occurring expressions. If X asserts that X has the property P, then means that property P holds for all X, or in other words, that everything has the property P. With it's called a universal quantifier. On the other hand, means that some X has the property P, that is that there is at least one object having the property P. Then is called an existential quantifier. Examples: any friend of Martin is a friend of John. Peter is not John's friend. Hence, Peter is not Martin's friend. In France, one above can be represented symbolically. Here, fx, y means that x is a friend of y, while m, j, and p denote Martin, John, and Peter, respectively. Next, all human beings are rational. Some animals are human beings, hence some animals are rational. In France, two above can be represented symbolically. Here, it's R and A designed the properties of being human, rational, and animals, respectively. Next, the successor of an even integer is at 2 is an even integer. Hence, the successor of 2 is at inference 3 can be symbolized as follows. Here, I, E, and D design respectively the properties of being an integer, even, and odd, as X denotes the successor of X and B denotes the integers too. Application of mathematics logics. Suppose we want to prove that following statement. If x plus y equals 16, then x is greater than or equal to x, or y is greater than or equal to x. If x is less than x and y is less than x, then x plus y is not equal to 16. Answer theorem. If x plus y equals 16, then either x is greater than or equal to x or y is greater than or equal to x. Proof by contrapositive. We prove that if x is less than x and y is less than then x, then x plus y is not equal to 16. To see this, note that x plus y is less than x plus y. X plus y is less than x plus x equals 16. So x plus y is less than 16, so x plus y is not equal to 16.